We'll begin today with Dr. Sasha Stump providing a brief overview of the Safer Products for Washington program and our criteria for safer, feasible, and available. Sasha's overview will be followed by a presentation on alternative work for architectural paints, sealants, caulks, adhesives, and hard surface sealers. After all three presentations, we'll stop the recording and take a 5-minute break. When we return from our break, we'll answer questions from the Q&A, and then we'll take verbal questions from anyone in attendance. When we're sharing information, we ask that you stay muted so everyone can hear. And with that, I'll turn the presentation over to Sasha.
Thank you, Wayne. And hello, everyone. Thanks for joining us today. I'm turning my camera on briefly again so that you can put a face to the name, but I'm going to turn it off while I present to save bandwidth and ensure my voice comes through clearly. My name's Sasha Stump, and I'm going to start our webinar today by sharing a short introduction on Safer Products for Washington. Safer Products for Washington is a program that was established in 2019 to implement Chapter 70A.350 RCW. The goals of the program are to equitably reduce exposure to toxic chemicals from consumer products and prevent their release to the environment. Restrictions and reporting requirements implemented by the program are adopted in rule under Chapter 173337 WAC. We implement the Safer Products for Washington program on a repeating 5-year cycle, which is divided into the 4 phases that you see on the slide. In phase 1, we identify priority chemicals and classes of chemicals to focus on. In phase 2, we identify priority products that are significant sources or uses of priority chemicals. Then in phase 3, we determine regulatory actions for those priority product and chemical combinations. And this is where we're at in our current cycle. Finally, in phase 4, we'll work to adopt the regulatory actions from phase 3 into rule. Once we complete phase 4, we then go back to phase 1, and this 5-year cycle repeats. We're currently in our second cycle of implementation of our program, and you can see the dates that we expect to complete each phase of this cycle on the slide. And as I said, we're currently in phase 3 of our implementation process, and so we're working to determine what regulatory action we'll take for chemicals and products that we identified in phases 1 and 2. If you'd like to review our full rationale for why we listed the priority chemical classes or the products that we'll talk about today, I encourage you to refer to our Cycle 2 Phase 1 and Phase 2 reports, and links to these reports will be shared in chat. Okay, so as I just mentioned, we're currently in Phase 3 of our process, where we make regulatory determinations for the product chemical combinations that we've prioritized this cycle. When making regulatory determinations for priority chemicals and products, the department has 3 options to choose from. Our first option is we can restrict the use of a priority chemical in a priority product. Our second option is a reporting requirement where manufacturers would have to report to ecology when they use a priority chemical in a priority product. And our third option would be to take no action. Now, if we propose a restriction, we must also show that safer alternatives to priority chemicals are feasible and available, and a restriction would either reduce a significant source or use of the priority chemicals, or that the restriction is necessary to protect health of a sensitive population or species. You might ask yourself, how do we go about determining what is safer? Well, safer is defined in our statute as less hazardous to humans or the environment. With that in mind, we developed a framework called our criteria for safer to evaluate and compare the hazards of chemicals. Some of the hazards we consider are listed on the slide, and they include things like chemicals associated with cancer, developmental toxicity, aquatic toxicity, or persistence in the environment. When we're looking for alternatives, we're looking for chemicals that are safer than the hazardous chemicals that we've prioritized for work in the program. And we think of safer as a spectrum. And so in our criteria for safer framework, we set hazard tiers along that spectrum to indicate significant steps towards use of less hazardous chemicals. We call these tiers our minimum and our additional criteria. These tiers align with scoring other hazard assessment methodologies, and this lets us leverage those other assessments to inform our work. For example, chemicals evaluated using the green screen methodology that scores benchmark 2 meet our minimum criteria for safer, whereas benchmark 3 chemicals meet our additional criteria. In addition to green screen, we also refer to other hazard assessments, such as those developed by Cyvera and ChemForward, as well as other resources like the EPA Safer Chemicals Ingredients List, or SKIL. For more information and details on our criteria for safer, please refer to the documentation that we'll link in the chat. In addition to identifying safer chemical alternatives, we also look to see if we can identify safer material or process alternatives. This is because the statute also defines safer to include a change in materials or design that eliminates the need for a chemical alternative. Although this won't work for all chemicals or products that we look at, these types of substitutions can be some of the more preferable ways to reduce the use of hazardous chemicals. An example from our past work in the program is when we highlighted digital receipts as an alternative to the use of bisphenols or other chemical developers in thermal paper receipts. Another example is using washable fabrics for certain applications rather than coating fabrics with something like PFAS to add stain resistance. These alternative processes or materials can work in some applications, and so they offer alternative options to consider in addition to reformulating products to use safer chemicals. I also wanted to briefly mention what we mean when we say feasible and available. We define these by referring to the Interstate Chemicals Clearinghouse Alternative Assessment Guide. Feasible means the alternative is either used or marketed for the application of interest or another similar application. Available means the alternative is currently used for the application of interest or is sold for that use in an application used in that application at a price close to current. In practice, this means we look for products on the market that already use the safer alternatives that we've identified because that's good evidence that they're feasible and available for use in that product type. A few last notes before we move into our presentations on specific products. First, it's important to be clear that while you may see products, trade names, or organizations listed on the slides you'll see today, these do not imply endorsement by Ecology. We often refer to existing trade names or products on the market as a way to demonstrate feasibility and availability for alternatives, but these are meant as examples only. Second, the information on alternatives and potential regulatory actions that we'll share today should be thought of as a snapshot in time and not as our final work product. We're still actively working to identify alternatives and determine if they are safer, feasible, and available, and some of our product categories are further along than others. That means that we also still have time to incorporate feedback and input, and so we encourage folks in attendance to share information that can inform our continued work. Okay, so that is the end of my short introduction. So now we'll transition into presentations from our Safer Products technical team on 3 product categories that they lead as part of our work in Cycle 2. The products we'll have presentations on today are architectural paints, sealants, caulks, and adhesives, and hard surface sealers. These presentations will be recorded and made available on our YouTube channel, so we encourage you to go back and refer to them as needed after the webinar. At the end of the presentations, we'll also have some time to hear feedback and answer questions about our process. With that in mind, I'll pass to our first presenter of all.
Thank you, Sasha. My name is Ivan Titale, and I am a Safer Products chemist in the Hazardous Waste and Toxic Reduction Product Program at the Department of Ecology. Thank you for being here. I am excited to share our update on the priority product of architectural paints. I will turn my camera off and begin my presentation. Next slide, please. The first priority chemical class for architectural paints was per- and polyfluoroalkyl substances, or PFAS. Revised Code of Washington, or RCW 78.350.010, Section 10, defined PFAS, or PFAS chemicals, as, quote unquote, a class of fluorinated organic chemicals containing at least one fully fluorinated carbon atom. In architectural paints, fluoropolymers, fluorosurfactants, and fluorinated solvent were all used. Fluoropolymers are primarily used as binders, while fluorosurfactants are primarily used as additives. As previously laid out in Cycle 1 Implementation Phase 3 report of Safer Products for Washington, key hazards of PFAS included carcinogenicity, reproductive toxicity, developmental toxicity, bioaccumulation, and persistence. Next slide, please. The second priority chemical class for architectural paints was octylphenol ethoxylates, or APEs. Examples of APEs included nonylphenol and octylphenol ethoxylates, while examples of APEs transformation products included nonylphenol and octylphenol. Key hazards of APEs and their environmental transformation products included endocrine activity, aquatic toxicity, and persistence. Next slide, please. We defined the scope for architectural paints in Cycle 2 Implementation Phase 2 report of Safer Products for Washington to include paints intended to be applied on interior and exterior surface of buildings and other structures by professionals or non-professionals. Paints, primers, and clear coats, such as varnishes or lacquers for wood application. And we know that due to this scope, we included wood paints as well for this product category. The following coatings, however, are not in scope: automotive paints, special purpose paints, industrial original equipment manufacturer coatings, as well as paints applied in factory settings. Next slide, please. As a first step in our alternative analysis, we defined the chemical functions of PFAS and APEs in architectural and wood paints. To obtain this information, we relied on technical reports from Cycle 2 of the Safer Products for Washington program, our current cycle, as well as a report by Organization for Economic Cooperation and Development, or OECD, entitled Per and Polyfluoroalkyl Substances and Alternatives in Coatings, Paints, and Varnishes, CPVs, report on the commercial availability and current uses. Next slide, please. Based on the two sources mentioned in the previous slide, we determined the following functions for PFAS in architectural and wood paints: durability, weather resistance, corrosion resistance, abrasion or scratch resistance, UV resistance, fire resistance, lubricity, oil resistance or repellents, anti-soiling, leveling, wetting, and as a solvent, that is U.S. Environmental Protection Agency, or EPA, volatile organic compound, or VOC exempt. While there are many PFAS chemicals that could fulfill the functions that have been mentioned, the specific PFAS that is U.S. EPA VOC exempt is parachlorobenzotrifluoride, or PCBTF. Next slide, please. Meanwhile, the functions of APEs in architectural and wood paints were as surfactant or emulsifier. These functions were then defined using the U.S. EPA Comtox functional use categories. These definitions were based on an OECD document on harmonization of functional use categories and US EPA's own added categories. The links to these resources are provided in the chat. Next slide, please. In addition to the two sources that were previously mentioned, we use the following additional resources when we perform an alternative analysis for PFAS and APEs in architectural and wood paints. Special Chem Note and UL Ultras Prospector were used to find chemical alternatives with the same functions as that of PFAS and APEs. We also use these websites for feasibility and availability analyses, specifically to determine the trade names of potential chemical alternatives. A Danish EPA report was used to find alternative chemicals to PFAS in architectural and wood paints. The report was entitled PFAS and Fluorine-Free Alternatives in Lubricants and Construction Products. Next, advertisement from companies were used for feasibility and availability analyses, specifically to determine the trade names of potential chemical alternatives to PFAS, or to determine example paints with potential chemical alternatives in their ingredients list. Some examples of these companies included Evonik, Micropowders, and Clariant, as well as the top 25 paint companies in 2025, according to Paint and Coating Industry or PCI magazine. Declared database and health product declarations were used to determine potential alternative chemicals with the same functions as that of PFAS and APEs. We also use these websites for feasibility and availability analyses, specifically to determine example paints with potential chemical alternatives in their ingredient lists. We consulted a textbook by Jones et al. Entitled Organic Coating Science and Technology to determine potential chemical alternatives to PFAS in architectural and wood paints. We also consulted both the 2025 Design Guidelines and Construction Standards issued by the Washington State Department of Enterprise Services, or DES, and the 2026 Standard Specification for Road, Bridge, and Municipal Construction issued by the Department of Transportation, or DOT, to determine if PFAS and/or APEs are specifically required to be used to comply with these standards. Comtoc's product use categories and collected data on functional use were also utilized to find alternative chemicals with the same functions as that of PFAS or APEs. The product use categories listed under EPA's Comtoc's platform are broad, but an example is given in the chat based on a keyword search of quote-unquote paint. And lastly, web searches were used to find example material safety data sheets or MSDSs of paint products. Next slide, please. We want to note a few things in the context of availability and feasibility. First, it is important to note, to remember that the Safer Products for Washington program is focused on safer alternatives rather than better than or equally performing as PFAS or APEs alternatives. This means that we look at currently existing paint components that provide the same functions as PFAS or APEs in architectural and wood paints. This also means that we look at additives as well as binders, particularly if additives could provide the same functions as those provided by binders. Second, as we understood them, neither the Washington DES nor DOT standards specifically require PFAS or APEs to be used to comply with the requirements. In our view, with respect to PFAS, tasks such as the AAMA 2605 is a performance standards, not compliance standards. These are unlike the NFPA 1971 standards that we encounter for our priority product of firefighting personal protective equipment, or the Class A fire standards that we encounter for our priority product of insulation. At the same time, we also recognize that fluoropolymers could perform better than PFAS alternatives for some applications and functions. Therefore, the use of fluoropolymers could lead to less repainting, as fluoropolymer paints could be more durable than non-fluoropolymer paints. This could mean less expenses for municipalities with limited resources that also use fluoropolymers for architectural paints of their buildings, and that switching to non-PFAS alternatives could lead to more expenses in the long run due to the need for recoating. In addition, we have seen evidence where buildings painted with fluoropolymers, such as municipal buildings, receive sustainability certification, namely the Leadership in Energy and Environmental Design, or the LEED certification, in the past, highlighting the use of fluoropolymers to comply with sustainability goals. However, we note that the examples we found were only for buildings from outside of the Washington state. Next slide, please. This slide contains the list of safer chemical alternatives that we have determined to meet ecology's minimum criteria for safer. This is part one of the table. While I would not have the time to go through every chemical line by line, audience can always go back to the recording of this presentation and hit pause to examine this list closely. Chemical names, their chemical abstract surface registry numbers or CAS-RNs, types, and functions are listed as the headers for each of the columns. Note that a chemical can contain more than one function, such as carnauba wax or ethylene homopolymer oxidase. Next slide, please. Here's part 2 of the table that contains safer chemical alternatives that met our minimum criteria for safer. Next slide, please. In terms of feasibility and availability, this table lists safer chemical alternatives, examples of chemical trait names, and examples of architectural or wood paint products that use safer chemical alternatives. This is part 1 of the table. And similar to what I said for the previous slide, audience can always go back to the recording of this presentation and hit pause to examine this list closely, as I will not be able to go through them one by one. Note that we omitted the company names for brevity. Further, note that the example product for one of the alternatives is based on a US patent. Meanwhile, we were not able to find example architectural or wood paints that use either isobutyl trimethoxysilane or triethoxyoctylsilane without the additional presence of PFAS in the list of ingredients. Next slide, please. And here is part 2 of the table. And note that we were not able to find an example architectural or wood paints that use hydrogenated castor oil. Next slide, please. Next, these are chemicals that we have determined to meet ecology's additional criteria for safer. Ammonium polyphosphate for the function of fire resistance, and carboxymethyl cellulose sodium for the function of lubricity. Next slide, please. And here are the results of our feasibility and availability analysis for alternative chemicals that met ecology's additional criteria for safer. Next slide, please. Our proposed safer alternative process was based on our previous works in safer products for Washington, cycles 1 and 1.5. Specifically, a safer process for the oil resistance or repellence function could be to clean the oiled surface with EPA Safer Choice certified cleaning products. Note that EPA Safer Choice certified products are considered as safer products according to our criteria for safer. Examples of such products are listed here, and note that we omitted the company names for brevity. Next slide, please. In summary, we believe that we have identified safer alternatives to PFAS and APEs in architectural and wood paints that met ecology's minimum or additional criteria for safer. We believe that safer alternatives are feasible and available for all the functions served by PFAS and APEs in architectural and wood paints. But we are still evaluating whether alternatives to fluoropolymer paints are feasible for infrastructure and monumental structures. Therefore, current information that we have collected supports a restriction on the use of PFAS and APEs for most applications in architectural and wood paints. Next slide, please. Things that we still welcome. Some of our current questions for this priority product include, are there examples of paint products that contain isobutyl trimethoxysilane, triethoxyoctylsilane, or hydrogenated castor oil without the additional presence of PFAS in the list of ingredients? To what extent are fluoropolymers or PCBTF used for architectural or wood paints in Washington state? Comments from contractors or municipalities are particularly welcome. And how are architectural paints different when compared to infrastructure or monumental paints? You can send your feedback to the listed email address. This ends my presentation, and I thank you for your attention. Please allow me to introduce the next speaker, Huckleberry Palmer.
Thank you, Yvonne. That's really amazing work. So next, we'll be reviewing Ecology's work on determining regulatory actions for the priority product of orthophthalates in building construction sites, sealants, caulks, and adhesives. Slide, please. Orthophthalates are diester derivatives of orthophthalic acid. Structurally, they consist of a benzene ring on which two ester groups are attached on adjacent carbon atoms within that ring. Of the approximately 30 orthophthalates that have been commercially produced, a subset has been commonly used as plasticizers, including plasticizers for sealant and adhesive products, including specific orthophthalate examples on this slide. Hazards of orthophthalates are described in detail in Ecology's Phthalates Action Plan. Human fetal exposure to some phthalates has been shown to be toxic to male sexual development and is linked to effects on brain and behavior. Phthalates can affect reproductive health in men and women. They can affect the metabolic system and are suspected of increasing risk for diabetes and obesity. Some are toxic to the liver and kidney or are identified as carcinogens by federal or state authorities. Phthalates can exhibit aquatic toxicity and accumulate in benthic organisms. Although phthalates undergo rapid degradation in the environment, widespread and consistent use has caused their presence to be a continuous environmental stressor. Next slide, please. Ecology has identified sealants, caulks, and adhesives as a significant source and use of orthophthalates. Specifically, we are determining regulatory actions for sealants and adhesives applied to buildings for construction or repair. This priority product includes a wide range of formulations and applications. A few applications are listed on this slide, but many more specific uses are common. This product scope does not include hard surface sealants or pre-assembled building products of which an adhesive may be a subcomponent. For the purposes of this priority product scope, caulks are a subcategory of sealants with relatively low elasticity. Next slide, please. Orthophthalates have been used as plasticizers to improve properties in some sealants and adhesives, typically comprising between 5 and 50% of the formulation when present. By lowering the glass transition temperature of the base polymer, external plasticizers like orthophthalates can impart improved softness, elasticity, low temperature properties, and other advantages. Orthophthalate external plasticizers do not chemically bond with the base polymer matrix and can leach out over time. Next slide. Because of the variety present in sealant and adhesive-based polymer types and in building construction sealant and adhesive uses, the linear process of identifying chemical alternatives and then looking for priority product commercial examples of those alternatives did not seem the most expedient. Instead, we inclusively used available resources such as those listed on this slide to identify as many phthalate-free products in as short as time as possible. Then we evaluated non-orthophthalate external plasticizers identified in commercial products against our safer criteria. Slide, please. Which is how we came up with our current list of safer alternative plasticizers for sealants and adhesives. Not every external plasticizer we identified in a construction sealant or adhesive met our safer criteria. But our list has grown and we have done market research, and we are always looking to add to our list of identified safer alternatives. To date, Ecology has identified 185 specific safer commercially available construction sealant and adhesive products. Next slide, please. Safer available phthalate-free sealants and adhesives identified in bead-applied forms include silicone, acrylic latex, siliconized latex, and a variety of silane-modified polymers. Products identified include mainstream, cost-competitive, high-volume major brands. These are provided just as examples, and Ecology does not endorse or recommend any specific products or brands. Several different safer plasticizers are used in commercially available products, and many products on the market achieve required properties without the use of any external plasticizer. Identified safer products are used for general repair, window and door sealing, kitchen and bath, trim and molding, exterior joints, concrete and masonry expansion joints, roofing and gutter, HVAC, flooring control joints, and structural glazing, amongst other uses. Slide, please. Many safer phthalate-free trowel-applied adhesives were also identified, representing several polymer base types. Again, products identified include mainstream, cost-competitive, high-volume major brands. Again, these are provided just as examples, and Ecology does not endorse or recommend any specific products or brands. A range of safer plasticizers were found in use in commercial products, and many products achieved acquired properties without an external plasticizer. We identified safer products in use for panel and board installation, subfloor, interior carpet, wood floor, vinyl floor, tile and stone, interior finish, concrete and masonry, kitchen and bath, general assembly, vertical and overhead applications, roofing, extreme load floors, and outdoor carpet, amongst other uses. Slide, please. Ecology has identified safer, available phthalate-free options for building construction sites, sealants, and adhesives of many different base polymer types across a wide range of product applications. The diversity and range of available safer products supports regulatory action to place restrictions on orthophthalates in construction sealants and adhesives in Washington state. Slide, please. I'd like to thank everyone for listening to Ecology's Sealants and Adhesives Priority Product Update. Sealants and adhesives are used in a wide range of building construction, maintenance, and repair applications in Washington. In this cycle, Ecology has identified a diversity of safer, phthalate-free alternatives available on the commercial market. We're counting on collaboration from you on this call and other interested parties to help optimize our state's regulatory determinations for phthalates and sealants and adhesives. In particular, we're interested in any specific applications for which there might not be safer alternatives. Information on other safer alternatives that Ecology hasn't identified, including spray or hot melt application types, and in any general concerns or sources of additional information. Please do save your questions and comments on this topic for the reserved time following today's final priority product presentation. And now I take great pleasure in introducing my colleague, Sean Ziga, to update us on hard surface sealers.
Thank you so much, Huckleberry. Hello, everyone. My name is Sean Ziga. I am a chemist with the Safer Products team, and I will be putting my camera off to try to conserve bandwidth for this webinar. Today, we will be talking about the current chemical of concern, along with alternative chemistries and products that are associated with this priority product class, specifically PFAS in hard surface sealers. Next slide, please. Our definition defined in our statute states that PFAS substances or PFAS chemicals, these are perfluoroalkyl and polyfluoroalkyl substances, are a class of fluorinated organic chemicals that are consisting of at least one fully fluorinated carbon atom. Common types of PFAS that are found in this particular product category being hard surface sealers are primarily fluorinated surfactants and then secondarily, occasionally fluoropolymers. Hazards that are associated with PFAS substances include reproductive toxicity, carcinogenicity, developmental toxicity, bioaccumulation, as well as persistence. Next slide, please. As it pertains to scope, here we define hard surface sealers as products that are intended to seal hard porous surfaces, and they provide a barrier as a barrier for protection from liquids and soils. Non-exhaustively, this includes products or subcategories such as concrete, hardwood, linoleum, stone, tile, and vinyl as well. Next slide, please. As it pertains to the resources that were used to identify the function of the priority chemical in this priority product, a review of the scientific literature, along with a review of various authoritative sources such as the previously referenced EPA computational tox or CompTox functional use categories and their database. Other functions that were not necessarily listed as PFAS functions, but can perform similarly in both function and capacity, were mapped to existing PFAS functions for the sake of identifying alternatives. Next slide, please. Functions of PFAS here in this particular product, hard surface sealers, are used to confer water repellency. This is akin to waterproofing, surface modification, film former. Also oil repellency, stain resistance, oil resistance, or anti-staining agents, surface modifiers, sealants, film formers, and then dirt repellency, anti-soiling. That's matting agents, surface modifier, slip control agent, and film former. Next slide, please. For the identification of alternatives that were feasible and available, research was done using existing product alternative databases and ingredient marketplaces such as Special Chem and UL Prospector, as well as identifying manufacturer and retailer websites that contain products that are marketed as PFAS-free hard surface sealers. Next slide, please. The following chemicals here are listed as chemistries that would provide the function of water repellency and meet our or are likely to meet our minimum criteria for safer for the function of PFAS in hard surface sealers. Please do reference the webinar recording for more thorough evaluation of this table. And this table for water repellency consists mostly of silanes and waxes. Next slide, please. This table provides alternative chemistries that will provide the function of oil repellency, stain and oil resistance, as well as dirt repellency. Similarly, please note that this table can be referenced from the webinar recording. Next slide. As it pertains to product alternatives, these are example products using the aforementioned chemistries that replace the PFAS function of water repellency, along with associated trade names, chemical trade names. The existence of these products is indicative of feasibility and availability of alternative PFAS-free products. Next slide, please. This is a continuation of chemistries and chemical trade name alternative products that can be used in replace of the water repellency function for PFAS and hard surface sealers. Next slide, please. For dirt repellency, please reference this table regarding chemistries, associated chemical trade names, as well as example products therein that would replace the function served by PFAS being dirt repellency in hard surface sealer products. These products, we aim to cover a wide variety of product subcategories. So these would be including concrete, masonry, and various other matrix types. Next slide, please. As a process alternative, the quick and prompt cleaning of a given surface will mitigate the need for the use of various hard surface sealers as a product therein, therefore also reducing the need for use of a PFAS containing hard surface sealer. EPA Safer Choice certified cleaning products with 3 examples shown in this table provide an alternative process for the need that mitigate the need for the use of hard surface sealers on certain applications of hard surface sealer products. Next slide, please. Information associated with alternative products and ingredients that are obtained from ongoing manufacturing orders from ecology are currently underway. That information, once evaluated, will continue to inform our decision-making process. The purpose of these orders is to assess product ingredients that can potentially meet our criteria for safer, feasible, and available, with manufacturing orders having been sent out to 5 manufacturers at this time as of March 31st, 2026. And manufacturers do note have 6 months to respond to our orders. And upon that time, we will continue to use that to, as I had previously stated, inform our decision-making process for this particular product chemical combination. Next slide. Safer alternatives based off of our previously highlighted data are available and have been identified. These safer alternatives do meet our minimum criteria for safer, with alternative products being feasible and available and currently being marketed and sold as products that do not contain PFAS species. And that current information supports at this time a restriction on the use of PFAS in hard surface sealers. Next slide, please. I would like to thank you for giving me some time today to discuss our decision-making process regarding hard surface sealers and PFAS. We would like to get any and all feedback regarding feasibility and availability of alternatives, applicability of some of these alternatives for various subcategories, anything and everything. So please do email the Safer Products for Washington at ecy.wa.gov. Next slide, please. And with that being said, I appreciate you spending some time, and I will pass it to Wayne. Thank you.